Log on, tune in, find out. Another good idea from Cambridge.
Speaker is Diego Dominici from New York, State University of New York in New Paltz. He's presently at the Universität in Berlin, and he's an experienced researcher because he was supported by a research fellowship.
So they say.
Okay, he'll be talking about polynomial solutions of differential difference.
Okay, thank you, Walter. Thank you all for being here. I want to thank the organizers for all their hard work. The workshop is really, really interesting, and for giving me the opportunity for being here. I'm afraid I'm not going to talk about time-level equations or integrable systems or Lax pairs or anything exciting and new, so feel free to use the X's. There are 2 X's there, 2 of the size. Don't panic, or you can just take a quick nap. So this work is joint work with Kathy Driver from Cape Town and Kirsten Jordan from Pretoria. I was visiting there last November, and we did this together. So the equation that I'm going to refer all the time is this differential difference equation. It's sort of a creation operator that generates a sequence of polynomials, starting with p0 equal 1, and generating the whole sequence through 2 polynomials an and bn of degrees at most 2 at 1. So every time that you see a dd in the talk, it refers to that equation. That's the only equation that I had numbers, so you cannot get confused. And so there are 3 main questions that at least I have about these polynomial solutions. One was what is the asymptotic behavior of these polynomials? I talk about that in Hong Kong, and Adri is here, so he doesn't want to hear about that again. The other is what is the zero distribution of these polynomials? Well, with Walter, one day we'll probably finish that work. And the third one is the one that I want to talk about today, and it's about the zeros and how the zeros interlace. So just a quick remark, there's no question about the existence of uniqueness of solution here, because obviously you can generate the sequence and you get only one polynomial sequence. Now, if the polynomials will be orthogonal, then there will be no question. We all know that the polynomials will have real zeros, the zeros will be simple, and they will interlace. However, many of these polynomial solutions are non-orthogonal, and yet they have similar properties in the sense of having simple real zeros and interlacing. For example, if you consider the Bell polynomials that you may know, or otherwise you will see the definition in a minute. This is the Bell polynomials with degree 5 and 6. Red is degree 5 and green is degree 6. You will see that they have a common zero at x equals 0, and then after that the zeros interlace. So they are not orthogonal, but they are close to having some properties of orthogonal polynomials. So the question was, is that true in general, and what can we say about that? So all the classical orthogonal polynomials satisfy these equations, like Jacobi, Laguerre, and Hermite. That can be shown easily through these contiguous relations for hypergeometric functions, at least for 2f1 hypergeometric functions. But then there are families of polynomials that are not of hypergeometric type, and they satisfy this type of equations. One is the Bell polynomials that I just referred to. These appear in many combinatorial problems or in problems related to analysis of algorithms. These problems appear related to the inverse error function. When you want to compute high derivatives, you come up with certain relations involving these polynomials. The so-called Eulerian polynomials also appear in combinatorics, and the Euler-Fermi polynomials that appear many times in the theory of splines and interpolation problems. And so none of these is of a hypergeometric type, so they don't follow from those identities for 2f1s, but they satisfy equations of this type. So the question is, what can we say about the zeros of polynomials of this type? So one question is, are they orthogonal or not? Because if they are orthogonal, then there is nothing to do. So there is a result by Al-Salam and Chihara that is not quite the same as this one. You see here they consider a polynomial times the derivative of Pn, but the polynomial doesn't depend on n, so it's a little bit more restrictive. And also they start assuming that the sequence is already orthogonal, and then they come up with the conclusion that the only solution can be the classical orthogonal polynomial. So it's not quite the same as saying, well, if I have a solution of this equation, are they orthogonal or not? So I tried to come up with some test, at least, to see if the family is orthogonal. And so here's a possibility. If you start with a solution of this equation, and the polynomials are monic and orthogonal, you can see that you have some compatibility conditions playing around with the differential difference equation and the three-term recurrence relation. So that's one of the equations. And this will be the other one. And you can solve for little bn and cn. This is what bn should look like. And then replacing here, you can easily solve for cn. I didn't write the formula because it's quite big. And so you can see that this is quite restricted because an and big bn are polynomials. And so they have to be in such a way that when you do all these operations, you come up with constants. And that's not something very easy to do. So for example, if you try for the Bell polynomials with those coefficients, you will end up with little bn equals 0. That's OK. But then little cn will be minus nx. So that's unacceptable. You expect that it will be a sequence of constants. And the same for the other ones. So these are clearly non-orthogonal. Are they maybe multiple orthogonal? I don't know. So some previous results, and if I'm omitting work of anybody here, please, I apologize, and let me know after the talk, so I know. There was some work in the 90s by Wertheim on Euler polynomials.
May I interject for 1 second?
Yeah.
When you say they are not orthogonal, you may prove that, or you don't know the orthogonality?
No, they are not orthogonal with respect to a positive measure.
That can be proved.
Well, that's what I showed in the previous slide. Yeah. So they consider these coefficients n and bn, which are sort of a generalization of the Euler polynomials. And then Dubois and Savoy did some work on generalizations of the Euler-Frobenius polynomials. So they consider these particular cases. And some Hermite-like polynomials. The most complete approach was very recently by Liu and Wang, where they analyzed this slightly more complicated differential difference equation. And they come up with the conclusion that the polynomials form a Sturm sequence, but under some restricted conditions, like the polynomials will have non-negative coefficients, or the coefficients will be alternating in sign. And that, in general, a priori is very difficult to check unless you have a family for which you know the coefficients. And so, as a test, is not the best that we can want. And so, first of all, which sequences of polynomials will be solutions of equations of this type? Well, you can try to solve for big an, big bn from these equations, but that's quite complicated. So we came up with a quicker test based on the roots. Okay, so if you define the roots of Pn by x and k, and then you consider this ratio, you can see that you have two equivalent conditions, and that follows right away from this equation. Either the polynomials an and bn will exist, and they will be unique for n greater or equal than 3, and equivalently, you can find a quadratic polynomial satisfying this relation. So that gives a very quick test on when polynomials will satisfy equations of this form. We assume that Pn has simple zeros for the proof of the term, but that's not really relevant because you can always remove the double zero and obtain a new sequence with simple zeros. Okay, so one example of an orthogonal sequence that doesn't satisfy this type of equations was in the book by Murad Ismail, and it's the following. Suppose you consider a family of polynomials with this Freud-type weight. Okay. Then now an and bn are not polynomials, they are rational functions. And these coefficients, little n here, are the coefficients in the three-term recurrence relation. These are orthonormal polynomials, so only one coefficient appears there. They satisfy some string equation that Walter knows about because it's one of those point de vue. Then you need some initial conditions for an so that P1 will have unit norm. Anyway, the question is that you can compute P5 and then you can compute the roots exactly. And so you can try that previous term to see if these polynomials will be solution of something of that form, now with polynomial coefficients, not rational functions. But when you do that, it doesn't work. And so that still opens the question to see if it's possible to find a family of orthogonal polynomials satisfying these equations that are not one of the classical ones. Okay. So in order to come to the main result, it is convenient to rewrite the equation introducing what we call sort of an integrating factor. So you want to write it as the next polynomial is the derivative of the previous one in some sense up to some factor kn. And so you do that by introducing this function kn of x, which has the integral of the exponential of the integral of the ratio of bn and an. And since an and bn are polynomials of degree at most 2, it is easy to classify all the possible integrating factors that you get for these equations. And so all you have to do is to look at the zeros, and we're going to do that next. And just notation, we want to work on the extended real line. So if you see something of the form f at infinity is equal to 0, that just means the limit. All right, so if Kn is defined by that equation, and you denote the set of zeros by Cn, then the term is that you cannot get at most more than 2 zeros on the real line, on the extended real line, including plus or minus infinity. So we chose an to be monic. That's not a big restriction because the ratio will destroy the coefficient here, so you can always rescale. And let me go quickly over the proof. So you have different possibilities depending on the number of zeros that an and bn will have. So if an has 2 different zeros and bn is just a constant, then kn has this form. And you can see that what are the possible zeros? Well, it depends on this being positive or negative. And in that case, you would have either zeros at lambda n or cn. So there is only one zero there. If you have a repeat root, then now kn has this form, and this blows up at x equals lambda n, so there is a 0 there. If an will have 2 zeros and bn will have 1 0, then this is expression for kn, and again you can locate the zeros. And if one of the zeros is repeat, you get this. And again, anyway, you can see that all the time you go at most 2 zeros in all these cases. And again, 2 zeros repeat and one that is not the same. Now, in the case when an has only 1 0 and bn has only 1 0, then you allow k to have zeros and plus or minus infinity. We are going to see examples of that with the Laguerre polynomials. And if the zeros are repeat, then you could also have zeros at plus or minus infinity plus an extra 1 coming from a. And in this case, when a is a constant, then you have a quadratic exponential, so you could have possibly zeros at both plus or minus infinity. So you really can classify all the possibilities. And based on that, you come up with this term that is not very difficult to prove. It's just a little bit technical, involves a lot of details. You have to be careful that the intervals where the zeros are located keep expanding. If they don't expand and start repeating at one of the ends, then you don't have interlacing at that end. That's what happened with the Bell polynomials. So these are the assumptions. Kn is continuous on the closed interval, differential on the open. That's so that you can use Rawls' theorem there. And if Kn has two zeros, then all the zeros of Pn and Pn minus 1 interlace. If Kn is equal to 0 only at one point, but then this prefactor in the expression of Pn plus 1 is equal to 0 at some different point, and those points, as I said, keep expanding, so getting bigger and bigger, then the zeros interlace. If not, if at one end you keep repeating the same zero all the time, like in the Bell case, then all you can say is that the zeros of Pn will be real and simple, but you cannot talk about interlacing, at least not for all the zeros. And finally, in this case, when Kn is not 0, but this ratio has two zeros, then you can talk again about interlacing. Now, one of the questions I have is, what happened next? I mean, if you are not in any of the cases, then can you conclude right away that the sequence will have complex zeros? It's not that easy to come up with sort of the last point saying otherwise, then there are complex zeros. So some examples to show how the theorem applies. For the Hermite case, which is probably the simplest case, Kn is e to the minus x squared, so this has zeros at plus or minus infinity, and that right away tells you that the zeros are on the whole real line. Nothing really surprising there. For Laguerre polynomials, well, now you have one parameter, so you may have one restriction. So Kn is given by that, and you can see that this will have a 0 at plus infinity, but then there will be a 0 at 0 depending on the sign of this coefficient here. And so you have a restriction on alpha, which if you want all the sequence to have zeros between 0 and infinity, translate to the usual condition that alpha has to be greater than minus 1. For the Jacobian polynomials, now you have two parameters, so you have more conditions. That's Kn, where that's kappa. And so now you need to restrict alpha and beta to be greater than minus n plus 1. And again, if you want the whole sequence to have zeros between minus 1 and 1, then alpha and beta has to be greater than minus 1. Nothing new there. So what about these polynomials that other people were considering for, say, these special values of an and bn? Well, you run the theorem very quickly, and you come out with this expression for Kn. And so that sort of gets the same conclusions that they obtained, but through a, in our view, more simpler approach. They came up with a lot of complicated calculations. What about 2f1s? So if you consider polynomials defined by that 2f1 function, then those are the coefficients now. This is k, and so you need to consider the possibilities of this being positive and that being positive. And that restricts n to be in that interval for interlacing. And Cathy and Kirsten came up with the same approach by using a completely different technique. And also you can look at the work of Alfredo De Agno and collaborators, and they come up with very similar conclusions by using Sturm sequences. So some of the results are not new. The possibility of adopting that you can put them all under the same umbrella. So with one result, you can capture results that before were in different papers using many different methods. Okay, now for the non-orthogonal polynomials and non-hypergeometric, what can you say? Well, for the Bell polynomials, with these coefficients an and bn, you have Kn equal e to the x, and the ratio a over k will have a 0 at 0. So you conclude that the zeros are in the interval minus infinity 0. But you cannot talk about interlacing because this 0 is fixed. It doesn't move with n. And so that's what you saw from the first graph. The 0 at 0 is fixed for all the polynomials. You can easily remove that 0 at x equals 0, and then you have a family with proper interlacing. For these inverse order polynomials, you compute Kn, and now you have an exponential, a quadratic exponential with positive coefficient. The term doesn't apply. As I said, there is no case for saying in that case you have complex zeros, but it seems that it should be. and this is an example. In this case, all the polynomials are purely imaginary. If you do a switch by changing the variable from x to I times x, then you get polynomials with zeros on the real line between plus or minus infinity. For the Eulerian polynomials, you can, again, compute Kn. And now you have a real and simple zeros between 0 and 1. But again, at x equal 1, you have a fixed 0, so you cannot talk about interlacing at that end. If you remove it, then you can. So, on the last minute, some questions. The first one is, can you find non-classical orthogonal polynomials that are solutions of this equation without having to add more coefficients or higher derivatives? Is there a Hubbard term in the sense of without assuming that the polynomials are orthogonal and then come up with some conditions, just looking at an and bn, coming up with conclusions for the polynomials being orthogonal? Is the converse of our main term true? Can we say that if none of the cases are true, then the polynomials will have either complex solutions or they will not interlace? This is something that I'm very interested in right now. What about equations of this form, contiguous relations for higher hypergeometric functions? It seems that there should be in the literature, and everybody keeps saying that it has to be. ASCII said, well, just look and you will find it, but we don't find it. What we find all the time is sort of annihilation operators, operators that reduce the order of the polynomial, but for creation operators it's not that easy. Even for 3f2s we haven't been able to come up with one, and even less for higher orders. This will be very interesting because there are several 3f2 sequences in combinatorial problems that could be attacked through this procedure very quickly. The only possibilities that people have been using before are Polya sequences or Sturm sequences, and those are quite complicated. And that's it. Thank you very much.
Questions? Your polynomials with the inverse error function, the zeros are on the imaginary line. Do they interlace on the imaginary line?
Right, if you flip now to the real line, they interlace.
They still satisfy this.
I will talk about those in Lloyd.
All right. More questions? Not. Let's thank the speaker again. And